Yes, so hi everyone. So you're the survivors actually. Thanks for being here with us for this session about Hyper. So I'm here with Tobias Mühlbauer. So he's our very own development manager for Hyper and co-founder of Hyper actually. So we're really happy to have him with us today. My name is Nicolas. So as you may have already found out, I'm not German. So I'm a pre-sales based in Paris. And I'm here to talk to you a bit about customer stories and also introduce you this session. Okay? So first of all, this is a technical talk. So be aware of that. It's intended for technical audiences, data engineers, DBAs. We won't show any demo here. We will dive into hyper architecture. So that's what it is about. But before starting, I would like to share a little story with you, actually. A journey about database performance, my journey to database performance. So it started 10 years ago. Well, I was working at an internet provider in France, and I was in the dev team responsible of the homemade CMS. I don't know if you know what a CMS is, a content management system. So basically, it's an application which is handling the content that is published on web servers, of companies. So it's pretty huge application, write heavy, and so my role there was to take care of the MySQL database, and it was that huge and complex transactional model. And if we go back in time, 10 years ago, I didn't know that much about databases architecture, and I didn't know what happens to SQL queries when they get pushed back to the system. So one of my responsibilities there was to guide new functionalities, and especially one which was to turn out this data into content analysis. And well, as I said, I didn't know that much about database architecture, so I was sent to training. And there is a thing very important I learned, I want to share with you, is the life cycle of a query. And it's important to understand why Hyper is so different. So basically what happens to a query when it is submitted to a database engine. So it gets parsed first. So your database engine will check the SQL grammar and try to turn it into steps, actually. And that's what we call plans. So it will build different execution plans, of course using its own internal architecture to scan rows and IOs and so on. And then a very important step is to optimize, of course, those plans to pick up the best one among others. And finally, to execute it in a more efficient way, if it can with parallelizations. And the thing is here, legacy database system all rely on the same architecture to treat those same steps. So this pattern actually is treated by a disk-based architecture when all you try to do is to minimize the IOs. So of course there is a lot of optimization techniques, and that's what my journey was all about. I mean, I spent days, weeks trying to speed up things by optimizing the data structures, using partition, indexes, storage types. But in the end, denormalization, just as you're looking at it. But in the end, it ended by just separates the database engines actually to obtain the best performance for both the transactional workload, the one we've talked about, and the analytic one, the new one that we're expecting to deliver. And that's really important, and it resonates with when Tableau acquired Hyper back in 2016. It really resonates with my story because when I saw what they've developed and basically how they completely revamp this framework, I found out it was really awesome. So now I will let Tobias tell you more about what is Hyper.
Thanks, Nicola. So what I want to do today is talk about what Hyper is, where it's coming from, what our experience is from being in production for 6 months now, and then give a very, very short outlook on the future. I can't say a lot, but I can say a few things that are coming next. So where is Hyper coming from? Hyper started around 10 years ago as an academic project at TU Munich in southern Germany. That's about the time I also joined the team, right, and have been with Hyper ever since. And what we set out to build was the next generation database system. And this sounds very simple, but it is actually not, right? Databases have been around since the 70s, 80s, and at least the ones we know today, right? And we started to question all the design decisions they made and rechecked and revalidated if they still make sense on modern hardware in modern days with modern requirements, right? And this led to a lot of academic success. We published a lot of papers. We built a system in academia. It became more and more mature. And eventually, companies would approach us at conferences via email and said, hey, where can I buy that? Can I license it? Can I get it somewhere, right? Why don't you just open source it? We took another round. We formed a commercial spin-off, and that was acquired by Tableau in early 2016. Now, what we did then was build a Europe R&D center. We have now over 20 employees based in Munich. That's the first real dev office that Tableau has outside the United States and Canada. So our dev offices are in Seattle, Vancouver, Austin, and then here in Munich. And what we worked on first was to replace the Tableau data engine in the existing Tableau products, and that happened with 10.5 earlier this year. And then the rest of 2018, well, it's not over yet, but we also did data engine for Tableau Prep that we released later, and we improved existing scenarios and evaluate new use cases, because out of the big scope of things we can do with Hyper, we are only using a very small fraction right now. So we are really interested in seeing what can we do next, right? How can we leverage Hyper better for your use cases? So as I've said, right, with Hyper we set out to build a high-performance next-generation database system, and we did that by basing it on 4 key design principles. We wanted it to be one system, operating on one state, making no trade-offs, and causing no delays. Now in detail, that means that we want to have one system where we do transaction processing, data ingestion, analytics, and other workloads. We want to do it on the same state to allow more real-time data analytics. Right now, you have an ETL phase coming from your operational system into your data warehouse, causing delays, right? But working on the same state in one system would allow you to be up to date on the most recent state of your data. We also wanted to make no trade-offs. There's a few things in databases that were questioned, maybe rightfully so, but in the end people found out they really like them, right? They like to keep them. So unlike the NoSQL movement or other specialized systems, we made no trade-offs when it comes to the SQL language support. SQL is a fairly battle-tested language, declarative language, that it really comes in handy for analytical query processing and working on relational data. And the other thing is ACID transaction guarantees. Having that atomicity, that consistency that those transactional systems bring is actually a great thing, right? And we didn't want to give that up. But at the same time, we also don't want to cause delays, right? We want to be as fast as we can go. Now, Hyper in 10.5, when we shipped earlier this year, was replacing the data engine. More concretely, this means we are using Hyper for extraction. So whenever you create an extract, you will use Hyper, and when you do federation. And the way it works is quite simple. Tableau products would send queries to Hyper, and Hyper would provide answers back. and at the same time it's leveraging Hyper to ingest the data it gets out of your source systems. And then in 2018-1, we also shipped Hyper as the data engine for Tableau Prep. So what you've seen in the keynote, all these flows that are coming together and modifying your data are happening in Hyper. Now, what are the immediate benefits replacing the Tableau data engine as it was with Hyper? We did a lot of testing. We used Tableau Public intensively. Tableau Public has over 1 million workbooks uploaded, right, which is a good battleground, and we did a lot of testing there first. We also did testing online, and then, of course, we asked customers in alphas, in betas, to gather data on how Hyper performs compared to the TDE. And what we saw on the really grander scale was that we can provide much faster analytics on data of all sizes compared to TDE. Now, one thing to note is that this is not true for every very specific case. So, of course, there's cases that deviate from that average. And if you happen to have a case, right, where you experience a regression compared to 10.4, please talk to your sales consultants and to support. Those things will come to us, and it's super valuable for us to find these things that we didn't catch in our testing. The second is data freshness. Hyper, by its nature, has a very different way of ingesting data and creating these extracts, which allowed us to be much faster there. In fact, we think we can be as fast as your data source allows. So we can be as fast as you can pull the data out. And the last big benefit we see is the improved scalability and overall performance, scaling to more cores, to bigger hardware that was not possible before. Now, we've been in production for almost half a year now, and we launched in January, and in March we already processed over 1 billion queries with Hyper in Tableau Online. So that was a really big milestone. And the last 500 million queries of that billion were processed in less than a month. So adoption was really catching up, right, accelerating, and I don't know how many queries we process now. It would be a huge job to run that over the logs to actually know the exact number. So that's actually when we stopped with 1 billion, and we know it's accelerating. Some learnings from production were that we continuously have to improve performance. It never stops, right? In our testing, we optimized for all these cases. There was thousands and thousands of workbooks. We thought that's probably representative of what everyone does, but Tableau is a very powerful tool, right? You can write very complex calculations. Everyone has different data set characteristics, right? Some people have more columns, some people have more rows, some people have more text data, some people more date data, right? So it's really hard to get all that up front. So we continuously invest in improving performance further and ship those with 2018-1, 2, 3, and we'll do so in the future. Then we've seen there's differences in extract file size. And this is the same as with performance. On average, we see that we are the same or slightly smaller than TDE files. But that's if you look at a very broad body of workbooks. So it can happen that there are extracts that deviate from the norm. And again, in these cases, we would like to learn from the regressions. And the third one is materialization of calculations. This is a big step we made, that we by default don't materialize calculations anymore on server when your extracts get refreshed. And there still is a way to keep that and to get materialized calcs back. The reason why we did not include it by default is that we didn't see the performance gains that we had with TDE. In some cases, you can now even see regressions. And what that means is if you materialize, it doesn't come for free, right? You now have that in your extract. Your extract is bigger. Your refreshes take longer, which is why we took them out. We're working hard on getting that resolved. In an ideal world, I would say we should not have that button, right? It should happen automatically. But we are not there yet. And the last one is resource usage and guidelines. That's what we're approached for very often, and that I can say we're working on. We're working on high performance guidelines for Hyper, for hardware sizing and these considerations. Now the next I want to talk about is why is Hyper so fast? And this is where it gets a bit more technical, a bit more geeky. It all starts with modern hardware and how it changed over time. The first thing I want to show you is memory prices over time. Starting in 1994 in this chart, on the x-axis going to 2016, and on the y-axis, and note its log scale, you have the price per megabyte of DRAM. Now what you can see is that memory prices are falling drastically, right, over the years. And main memory capacities have really grown a lot. Now can someone guess what a gigabyte of main memory would have costed you in 1996 when this chart starts? It's like, I mean, you can read it from the chart, but anyone has a guess? Yeah, so it's really expensive. It was $45,000, yeah. And you could barely find a machine where you could fit all that memory in, right? And today, you can get a gigabyte for around $2 or less with DRAM. And Intel, earlier this year, announced that they now also have this Intel Optane non-volatile memory. Other vendors are also releasing that kind of things. And that will also provide a bump to memory capacities again, because the notion there is you sacrifice a little bit of performance, but you get a lot more capacity on these DIMMs. So it will continue to grow. The second thing that changed a lot was CPUs, your processors. The good news is that Moore's Law is not over, so it still holds. You get exponentially more transistors with every generation. Now, the bad news is that the single core performance is stagnating. And that is because you have a constant power budget on your dies, and there is a lot of leakage. Now, what this means is that CPU vendors have to make the CPUs more and more complex. And that started slightly before these effects came really into play, where you had more superscalar pipelines and vectorization on your cores, right? But then the biggest shift was the shift towards multi-core scaling, which is the world we are in right now. And that will continue. So CPUs will become more and more complex, and they're already very, very complex things. And that is a big, big shift for software. Which brings me to what this means to database systems, right? So database systems have to be adapted for this new reality of hardware. What I'm showing you here is from an academic paper in the database conference, where the authors compared traditional engines like MySQL, which has a tuple at a time processing engine, which is the standard, right? Since the 70s, 80s, all the traditional database systems would have processed your query one record at a time. And on the y-axis here, you have a query execution speed. And you can see that the traditional engine, right, is not adapted to modern hardware. It's the slowest. Then what happened in 90s, 2000s was that people thought, well, why is that, right? And they found reasons, like virtual function calls and not being adapted to the CPU pipelines. And two ways out are what MonadDB did by materializing column at a time after each operator, which is the MonadDB approach to the right. And the same group of people also came up with yet a slightly better approach, which is processing vector at a time. So instead of asking for the next tuple, they would ask for a vector of tuples, like 1,000 at a time. And that also helped improve performance a lot. So more modern systems improved greatly. But then they also showed in the same paper that if you would pick a programmer, right, let him write a hand-coded C program for a query, he would beat all of those approaches. Now the thing is, and this is something where Hyper came into play, is we asked ourselves, why can't we reach that performance, right? Why can't we generate a program at runtime write software that does that. And that's actually what we did. So with Hyper, we don't execute the query itself, but we have a query plan, we optimize that, and then we take that query plan as a blueprint to generate code that executes the query. So Hyper by itself can be seen more as a compiler rather than a query engine. Now, why is compilation attractive now, right? You might say, why didn't everyone do that from the beginning? And the simple reason is that it didn't matter. And why it didn't matter, it has to do with latencies of access to data. To give you an analogy, I brought you the Latency Pyramid that is taught in computer science. And so assume that you need to sign a document. And one CPU cycle is 3 feet. Then having something in your CPU register means that you have your document on your table. You can sign it right away. The time to access your document is very low. If it's in the CPU caches, so there's an L1, L2, L3 cache, getting bigger or larger the farther out, means that if something is an L1 cache, it would be in your bookshelf, right? You have to go there, fetch it, sign it. Okay. L2 cache, it's in the room next door, still okay. L3 cache, neighboring building, so some way to go, but still possible. DRAM is already a block away, so really you have to make an effort to go there. But if you go to disk, then it's on the other side of the earth, right? And this is actually a long walk. Even with SSDs, this didn't improve that much, right? So you still have to walk a lot. Now what this means is that for decades, main memory sizes were not big enough, and database software was optimized for the disk case. Everything they had to access, it took a very long time to fetch, right? So the efficient processing was not that relevant. You could have compiled query plans, but if you have to access your disk all the time, it doesn't matter how fast that is, right? It will be shadowed by the high latency of your data access. And with Hyper, we aim to keep data as far up the pyramid as possible, and DRAM gives us a very good staging area there. And with growing DRAM sizes, we can keep more and more in DRAM, more of your relevant data, and that's where the efficient processing then really matters. Before I said that we create query plans still and we optimize them. With optimization there, I meant query optimization, the logical query optimization. And efficient execution is important. You can have integer factors in either direction, right, just by optimizing your query engine. But you also need a good logical query optimizer. And what I'm showing you here in the background in this viz is query execution times for different query plans you can pick to execute the same query. Now with that, I mean different join orders. Think about you have an orders table, you have a customers table, you have a region data where the customers are in. You have to join these 3 tables together. Now the thing is, how do you join them together? Do you first join the orders with the customers and then with the region? Or do you first join the region with the customer and then with the orders? And so on, right? You can enumerate a lot of ways to do that. And what this viz shows is different of these different enumerations, different ways you can execute that query plan. And it's all with the same query engine, all done with Hyper. And the execution times vary from as low as 10 milliseconds up to over 3 seconds. So this stuff also really matters. Now, why is that hard? It's a hard topic. It's very theoretical. And there is no perfect way to do it, which means that you need real experts in that area, and you need a lot of thought put into that. And there's only a very few researchers and practitioners in the whole world who specialize in that. Well, so why is Hyper good at that? And the answer is we are just lucky, I would say. One of the co-founders of Hyper, professor at TUM, and now principal advisor at Tableau, is one of these few researchers who focuses on that and is really an expert in that area. And so he came up with the original design of the query optimizer that is now part of Hyper. Now back to query execution. Parallelization, as I've said, is very important. If you only use a single core on your machine, you lose out on a lot of performance today. We looked at the parallelization that traditional databases did, and they scaled up to a few cores. Parallelization was added later as an add-on, but we found limits there. We found that you cannot scale beyond a certain limit, and that might be as low as 8 to 10 cores. Now with Hyper, we set out to build an engine that can scale to the large core counts you can find in servers today, which can be way more than 100. And to explain you how that works, the parallelization works, I bring you a cake analogy again. Everyone loves cake, right? So it's a nice way to think about it. And the cake represents your query, the query you have to process. Now, traditional databases would have eaten that cake, processed your query, by cutting it into 4 equally large pieces. If you had 4 eaters, 4 cores, and every person eats 1 piece. Now, the thing is, what if one person is slower than the others? And that's something in software engineering we call that skew. And that could be in the cake world because of hard-to-eat nuts. One piece is larger than another slightly. You're distracted by other work, right? You get called. And in the end, there is someone eating alone and everyone else has to wait. So your query is not finished. And the same is true for CPUs. And that's the result you see is bad CPU utilization. You're not as fast as you could be. And then the other thing is, what if new people arrive or have to leave or something happens, right? After you cut the cake, you lose out on flexibility. You cannot add more cores or take cores away as easily. So load balancing is much harder in that world. Now, why does skew really hurt you so much, especially with bigger core counts? There is a theoretical law for that. It's called Amdahls Law, which says that the theoretical speed up of a partly parallel task is always limited by the non-parallel part, which would be waiting for someone to eat his piece in the end, right? And if not all parts of your query execution are really fully parallelized, scalability can be severely limited. Now, an example here is if you have 32 cores and you only have 95% parallelization, which is already great, right? You would say, 95% of my query is parallelized, only 5% are serial. That's great. But then you have 32 cores and you will only see a 13x speed up over a single core. So you're missing out on a lot, right? You would have expected 32x speed up. It's only a 40% utilization. And with more and more cores, it gets worse and worse. So take 200 cores and take a 99% parallelization. So only 1% is not parallelized. You'll only get a 63x speed up, not a 200x as you expected. And that's just a 32% utilization. So the thing to remember is that if you fail to handle the skew, it's like not parallelizing at all. And the traditional way of query processing, parallelization and query processing engines, does not scale with modern CPUs. So how does Hyper do it? How do we do it? How do we handle skew? It sounds simple, and it really is that simple. We cut the cake into smaller pieces, many more pieces than we have cores, and we call those morsels. And then every one of the workers, CPU cores, will pick a morsel at a time, processes, and whenever they're finished, they would pick the next one. And that means that a faster eater just eats more morsels than others. And this way we got to Skew Resilience. Now, of course, it's much harder to implement that than it's shown in the analogy, but this is really the main thought behind it. And the other thing is that this is really hard to add to a traditional database system. So if you start from ground up, you can make that choice. But adding it later on is really hard. The other big advantage we have is that if a tastier cake becomes available, right, take a CEO query, you want to process that first for very obvious reasons, right, you can do that now. You just put those morsels to the front of the queue, people will pick it, and it gets done much quicker. And you can change the number of cores. If there is another software running, taking your cores, right, it finishes at one point, cores become available, you can take them for query processing. And this we tested on very big server machines, and it's shown to scale up to more than 120 cores, which is really impressive and about the size of cores you have in server systems today. Now the final thing I want to talk about is transactions and analytics. I said in the beginning that with Hyper we wanted to combine transaction processing and analytics. And that is because in the traditional world you have operational systems today, right? You do ETL into data warehouses where you do your OLAP queries. And then you have all these beyond relational stores for graphs, key value, data mining, Hadoop. And there is two fundamental issues we see with that approach. And the first one being that ETL delays your time to insight. And then the data stored in your beyond relational systems doesn't allow you to do a holistic analysis of your data. Right? You actually want to analyze it all together, and now you can't as easily. Which is why with Hyper, we really want to combine these things in one engine. And we currently focus on the combination of transactions, continuous data ingestion, and analytics, but are also looking at integrating more beyond relational workloads. And this is where our research group at TU Munich, which we still closely collaborate with, is currently looking into. Now for Tableau, right now that means that we are the new data engine. That the properties our engine has come in really handy. We use the right optimized part of Hyper for extract creation, for extract refresh, for federation, for Tableau Prep. And we use the analytical capabilities and the great read speeds for dashboards, for interactive analytics, for deep analytics. Now, what does it mean for you? For you it means that compared to TDE, that was last shipped with 10.4, you now have with Hyper a data engine that speaks SQL, not TQL anymore. I know we don't expose that yet, but it is of course an option we have now. And it's a language that many other people speak. It's no longer a language that was proprietary to Tableau. We leverage resources better. That's just because of the design of the query compilation, the parallelization. We can really leverage your underlying hardware. I brought you an example of a query running in TDE server and in Hyper-D. And you see that, well, TDE is using your CPU for 27%, right? And Hyper is really using 99%. And it's not wasting that, right? Hyper is done much quicker with that query compared to TDE. So you get faster response times. A big change for extraction was to leave out a lot of post-processing that TDE did. The traditional data engine would first gather all the data, buffer it up, and then in the end do post-processing to sort the data for compression, optimize, and then package. Hyper is done as soon as it received all the data. The extraction process is done. And this, of course, then scales much better depending if your source system can handle the speed. So that's why I think that the source speed is often a limiting factor. When it comes to storage, there are a few changes. In TDE, everything was a whole column was stored together, and it was really hard to add something to append to change within the column. In Hyper, we have segments, which we call data blocks. So we partition a column into much smaller pieces, and then we compress per piece. So we have a dictionary per data block and column, whereas for the TDE it was global, which severely limited scaling up the extract sizes. Both engines do lightweight compression, and with Hyper on top of that, we also do black box compression, meaning LC4 compression if it says something to you, on top of the lightweight compression techniques. And we only do that if we can see a big file size gain from that reduction. And the last thing I wanted to shed a light on was server topology. So in 10.4, you could have multiple data engines on the same worker. And in 10.5, there is only a single one. Now, this is not a step back. We want just one Hyper instance per worker, because we really want to use the resources as best as we can, and we can only do that if we consolidate all the workload on that one worker. And that one worker, of course, can have multiple extracts open and process multiple queries at the same time. With that, I want to hand back to Nicholas for some customer stories.
Thank you so much, Tobias. So, yes, just a few customer stories here. So, maybe just before starting, a short question for you guys in the room. Who's already using Hyper? If you can just, yep. And have you seen speed up and faster? Yep. Also, great. So here I brought an example from a customer of mine. So as you can see, you will see I bring back an administrative view within Tableau Server, which just shows us the fact that they extract refreshes are now 35% faster. So an average, it's an average again for TD extracts. What took 85 minutes now took 55 minutes with Hyper, and in that particular case, again, the source system is not fully tuned, so we still have optimization on that part. And other example for our very own Zen master, Rod Bradburn. So, can you tell when they've updated the server to Hyper? I guess it's pretty obvious if you pick up when the red dot disappears, which are actually the longest extract to proceed. So, yeah, so hopefully that's just a few customer stories, but the thing is, we really wanted your feedback. Us as SCs, as pre-sales, don't hesitate to talk to us. We will make sure to push the information to the development team. They really need all those feedback and your data. So if you're willing to share what Hyper, what are the new behaviors you're seeing with Hyper, even in the good cases, or if there are some trade-offs, yeah, to just don't hesitate to give your feedback. We really need it. Okay? So we're going to take some questions. Maybe you got for Tobias, and thank you.
That's great. So the extraction time went from 7 to 2.5. Mute the mic. I'm sorry. I will repeat. So the way I understood it is that from the query performance, right? It's not felt from the user base, right? Which is something that is true in many cases. Now the thing is, with Hyper, I see it as the first step to make Tableau more scalable, more performant. You can think about it as a car where you put in a really fast engine. Now, you also have to make changes to the tires, right, to the chassis. It has to be an end-to-end thing to really get the performance on the road and really feel it, right, and make it fun. And that's still something we actively work on. The good news is from the acquisition, we have a real database system, so to speak, a very powerful engine. We are using a very small fraction of what it can deliver, and we are working on expanding that. And then we are also working our way up the stack, right, to really analyze where it's lacking, right? When the customer experience is not great, with the fast engine. What is it now, right? It's surely something else in the stack that we can still improve. More questions? This time I will give the mic.
So I think I understand from from the graphics that Hyper is neither a row or tuple store, and it's not a column store. It's a column segment store. Would that be the data block? Is that roughly how you think of it?
I would say Hyper is a column store. It's just the physical organization that we in the columns, right? We would take 130,000 records roundabout, right, and make those a block. But I would still consider it a column store, just without the global compression schemes that span the whole column, which of course, and I totally see the point that if you take a whole column of many millions of rows, you can do very fancy things with that, right? But it also costs you a lot of pre-processing, right? More questions? Ha!
Building on from that, really, we saw using the TDE format, the Tableau data extract format, that it worked great a lot of the time, but then sometimes for incremental additions, it would really fall over and so on. And I think, based on what you're saying, that because of the way you're handling those updates, that's going to be more resilient.
Yes, that's true. Because the TDE had these very global encodings and global compression schemes, adding data was not as easy. And it oftentimes led to having to recreate that whole column to really get to the encoding we liked, right? Which caused us to fall over more easily there, yes. Now the thing with Hyper is that we can append data more easily. We're not leveraging it to its best extent yet, but also we are working on that. But we're already seeing great improvements.
Kind of following on from that one, is Hyper going to be, or looking at dealing with things like late arriving data better? So we have a lot of situations where we have a 6-week latency where we could have transactions arriving up to 6 weeks late. Now, right now, we can't do an incremental extract because their transactions are also, we have to do a full refresh every time we want to do that. So what we think like is things like partitioning, so where anything is over X period old, we don't have to process that anymore, we just process everything within a particular slice. Is that type of things you're looking at for putting into the product?
Yes, definitely. That is a bit orthogonal to which engine you use, but we make it easier to get to those sliding window kind of extraction processes that everyone likes. We are really looking into that. One way is to really engage with your sales consultants if you have pains in that area. Because from the Hyper side, we're looking at how we can expose it. Does it have to be the UI, or is a lower level API maybe right? Maybe you can do it through a lower level SQL API and really define your own custom ETL. So if you have pain in those areas, then this is definitely something we're looking at right now.
Quick question from materializing calculations and how you have to click the optimize button. Are there some calculations that you know of which you would want to materialize versus some you wouldn't? So should I say write all my string calculations first, optimize, and then just leave it after that?
The short answer is depends, right? Again, and it's really hard to say because our storage layer has a lot of deduplication and things, so that even there it's not often necessary to pre-compute. Even for a very complex calculation, it might not be. The things where we are seeing regressions, if you don't have materialized calcs, in many cases it's data preparation done within Tableau. So oftentimes what we see is that You have a string column and there is regular expressions on and then some very fancy date parsing to get to the dates, but then the visualizations only work on the dates, right? So in those cases, I would say there is a very good case for using Tableau Prep to create the right initial extract first, where you do analysis on. And then I agree, there will still be cases where the calculation is very complex and it makes sense to materialize. Where we want to get to is doing that automatically. Because as an engine, we know best when to cache something. And then also, the second advantage we get from that is that if you update your data, we might not have to compute the materialized result of that calculation up front, right? We could delay that until the first query that really needs it in these things. So this is something we're looking at to get to an automatic and then transparent way of handling complex calculations in the future.
So if you're, and I'm not sure who's best placed to answer this question, if you're no longer materializing the calculations, does that mean we've engineered our way out of the dreaded workbook extract out of sequence where the calculation is already defined in the extract? Do you know the one I mean? Where your workbook explodes with a whole load of red pills that say calculation underscore with the calculation number. And this is probably not something you're familiar with, Tobias.
Yeah, yeah, but it shouldn't. I mean, it shouldn't. I'm not 100% sure. Yeah. I'm not. Yeah, I'm not. To be honest, I'm not 100% sure. So.
Okay, so switching to Tableau Prep, and having done a little bit with it, it's doing some very cool things and so on, and it's doing a lot of stuff on the fly. Does that actually mean that you're using using Hyper as an in-memory database while we're doing things with Prep? And the second part of that question is, does that actually have some implications in terms of if we want a great flowing experience in Prep, we should consider how much data we're bringing into Prep versus our local memory?
That's a very good question, and I don't have a definitive answer to that. A lot of workflows, your data doesn't necessarily have to fit in memory because streaming from, say, an SSD is also really fast. Where disks really fall over is if you have random accesses to data. But if you stream through, they give you a quite reasonable speed that might be okay for really an interactive flow, right? But it's hard to say, right? Of course, if the file is cached in memory, it will be as fast as you can go, but is it really worth spending that much, right? Yes. We do. More? All right. Then I think we can call this conference done, right? And everyone have a safe flight back, unless you're in London.